When we give ourselves permission to fail, we, at the same time, give ourselves permission to excel. In this unit, we will learn one of the most popular clustering algorithms, maybe even the most popular one, k-means. This is a super fast algorithm, but to be honest, I'm not entirely comfortable with its popularity and prevalence because many times it makes mistakes. However, this algorithm teaches us something beautiful: to fail and to learn from failure. Seeing this technique, understanding why it makes sense to fail in order to excel, and also why sometimes that's not enough, and then this algorithm makes mistakes. All of these make for fantastic lessons in general algorithmics. Let's go. We will first describe the algorithm, and then we will analyze it. Algorithm description. Here is the algorithm. Look how simple it is. Step 1. Select k points as the initial centroids. A centroid is defined as the central point of a cluster. We don't have any clusters yet. That's okay. We therefore just start off with random centroids. Step 2. Form k clusters by assigning each point to its closest centroid. So, are these clusters any good? No. They are based on random centroids. Did we do a good job? No. So far, we are failing, and that's okay. Recompute the centroid of each cluster according to the points of the cluster. Here is where we use what we did, where we use our failed attempt to learn how to fix the centroids. Repeat step 2 until centroids don't change, or don't change much. Can you see where this is going? Let's look at this algorithm in action and see how very elegantly and quickly it solves the complex problem of clustering. Let's assume we have only two variables: white blood cells and potassium levels, or just X and Y. And let's assume we know that the correct number of clusters, k, is 3. Now, the algorithm randomly picks these 3 centroids. Naturally, these random centroids are not the right centroids, but as we said, it's okay to fail. By the way, note that the centroids don't necessarily have to be true points, as we see in this example. Now we form the 3 clusters around the 3 centroids. This is pretty easy. For each point, we just compute the 3 distances to the 3 centroids and assign the point to its closest centroid. So, this point is assigned to centroid number 1, this point to centroid number 2, this also to number 1, this to number 3, and so on to all points. And here comes the fun part. We see here 3 clusters: blue, red, and green. Notice how very easily we can compute their real centroids. For example, just by averaging all the x values and y values of the points that belong to a cluster. Alright, so as we can see, the computed centroid of the cluster is different from the centroid that created the cluster. The idea is that if the centroids have changed, the association of points to the centroids should change as well. And now, if the associations have changed, if the clusters have changed, the real centroids should change as well. But if the centroids have changed, the association of the points to the centroid should change as well, and so on and so forth. What we see is that after only very few iterations, we get to a point we reach centroids where there is no change of the association of points in comparison to the former iteration. So actually, there is no point in reiterating this step once again, since there is no source that has the potential, that is capable to make additional change. We reach convergence, and these are the clusters that the algorithm will output. And hey, we reach the output in very few iterations, 6 in this example. Look at the short evolution of the clustering process. So, this was the description of the algorithm. In the next segment, we will analyze it and discuss some very interesting features of its operation.